Yakov, do you have any experience with Hugging Face library or with transformers?
Yes, I started a few weeks ago to learn about transformers, and I made a lot of experiments, read part of the book, and quite impressed. Now, what I can say is that it looks that there is a balance between hiding complexity. Sort of when you start playing with the transformers, you find that they did a lot of good work, but there's also a lot of mess, say bad models around, and sort of when you get your hands dirty, you can find a lot of work over there. It's not because the library is not good, but because NLP is complex and difficult, and so sort of I think people should not be expecting from walking through the first chapter of the book that all the examples are easy to take over for their own projects within 2 or 3 minutes. There's some interesting work which you need to do in order to be really happy with that.
Yeah.
Yes, like fine tuning.
Mm-hmm.
So,
Yeah. I mean, the complexity builds off the way the book structures, the complexity of the way it is. For example, if you go further, the last chapter is how you can uh, uh, build language models from scratch, and also some future directions. So I think at the beginning is like somehow not that complex as you said, but the complexity increases when we move through the chapters. Yeah.
Now, I was referring to something which is even in the first chapter. So if you, for instance, take if you take the example, let me just point out one example. If you have the sentiment analysis, okay, let me, maybe I can share my screen. I made an experiment. Something I was very surprised about, something when I made my first experiments about over here. Okay. Now, if anyone wants to know how to run the sample notebooks in a free Colab cloud instance, I can maybe show this to the people who to join. That it's very easy to start up such an example and play with it. So I played with this over here, and I jumped to the text classification, and we took the standard pipeline text classification. And we get an output negative because the customer is unhappy.
Mm-hmm.
Okay, that's what the book says. Now I made an experiment over here. I take two sentences. One sentence is I live in Syria and I live in Iraq. And what happens is that one sentence, first sentence, gets a very positive sentiment, and the other sentence gets a very negative sentiment, and which is really doesn't make sense. What happens is that these two sentences are really neutral, and this particular classifier does not have a neutral state. And as a result, if he understands something clearly, he gives a high confidence, and he has to choose, he has to guess negative or positive, and it doesn't make sense. So if you take this classifier over here, for a real application, you will get for all neutral sentences, you will get noise of something very positive or very negative, and it's very confusing. Now, if you want to take a different classifier, there are other classifiers which have a neutral state in the middle, and they will tell you that's neutral. It's not positive or negative, but you have to find them. You have thousands of classifiers. So now you have to understand which models are good and which models are not good. And so to find
sort
out
of.
how good a model is.
So let me comment on that. I think it's not a matter of searching for a model that has neutral. What you would do is you would need to find the data. Maybe it's your data, and you'd need to fine tune the model with with a final layer for 3 classes, and your content then has to be your model has to be for 3 classes. And you actually don't need a huge amount of data. People have experienced this. I'm not sure, but because with transformers, you've got this huge base model you're using, right? When you instantiate your Hugging Face, your auto model or whatever, you got this huge base model that knows a lot already. And so sometimes you can get away with just 1,000 examples for each, or even a couple hundred, and get pretty good results. So You get that. It's not about finding the right model so much. It is about finding which base model performs best for you, but it's really about you having your own training set, and then all you have to do, even with using their pipeline, right, is well, you just train it with, and you just tell it the number of classes you want. You use their classification head. You say there's 3 classes, and then you run your, pretty much is all you do, and then you run your training set on it. That's how people, I think, use. Does that make sense?
Okay. Yes. So you're saying that now
that's actually, yeah. Go ahead. I'm sorry, please.
Now, what I was referring to is that, say, even if you search for a base model, you have to choose a good one, and having thousands of models on the hub, it's not always straightforward what is the best model for you. The whole point which I want to make over here is that you just read this one line over here, and doing this right, sort of to do actually the work which you need to do over here, you have to deal with quite an amount of data and a choice and possibility, and you should expect it to spend at least initially a few days to digest what's in the system until you connect with it. Sort of it's just like the tip of an iceberg. And there's a lot of things going on over here. That's what I can say. Sort of, I played with the first lesson and did something similar with a similar course, and it took me a few days until to actually felt not confused by all the things which happen behind the scenes that I see while I have a feeling over here. Sort of don't get, and in the end it's easy. In the end things are falling into place. But I just want to say is that if you start really playing with it, spend some time.
Yeah, thank you.
Yeah.
I think
I want to make. I guess. Yeah. So we are kind of starting, because we're actually, what's interesting is that's what the first chapter is addressing. Almost exactly what you're talking about there. Yeah. So they're trying to just orient you to transformers, but they don't really explain it very well. But they're trying to orient you to their framework, to the Hugging Face framework, which is exactly what you just went through, Jakob. So that's a good lead in. I would say I like to add one thing. Did you Jakob, on any of the models that you downloaded in the Colab there, did you do dot model so you can see the entire stack of the model? Have you done that?
No. Now maybe what I
would
suggest.
Let's do that right now. Can you?
Okay.
Can you open up your Colab? Actually, I have Colab opened up right now. So let me show you this. I want to make sure people.
Maybe we should maybe we should show the participants over here how you actually open up the notebook to get there. That it's very easy to. Okay, what I suggest is.
So does anybody?
Yes.
Does anybody here want just a quick tutorial on opening up a notebook in Colab, or is everybody past that point? If anyone wants to do it, I'll just do it right now. I mean, I have it open already, but it's very easy. You just
I guess everyone here.
Do you want me to do that? Would you like me to do that?
What I would say, maybe in just 2 seconds, you could say, if you go to the GitHub page of a repository and you change the name of github.com to github2colab.com, then the notebook will open up. That's sort of very short
what did you
description.
I mean, all I did, you can tell me what you did again there, but all I do is copy the URL for the notebook. This is the notebook, chapter 1.
Yes.
And you go to Colab. I already have Colab open over here, and then I think all you have to do is go. Sorry, I have a big lag time because I'm on satellite internet for you guys. Oops. That's not Colab. There you go. Sorry, my internet's kind of slow, but we'll get there. All right, so here's Colab is up now. This is you guys. And there's the pop-up for Colab asking if you want to open up a notebook. And all I did was, I think I just did, you choose GitHub, and I think just put in the URL, that for the notebook. Let's see if that works. It looks like it's opening it. So now,
Yes.
once you have Colab opened up, I mean, I just don't. You need to connect. You should probably connect to a GPU. So it didn't open, did it?
There is
Okay.
a
So what were you
shortcut
saying about that, Yakov? I guess I forgot how I did it the first time. So what do you have to do to make this work?
Okay, shall I share my screen?
Sure. Go ahead. Go ahead. What the heck happened? I guess
They also have much easier. They have a shortcut right in the GitHub. In the GitHub page, they have a table that lets you open any chapter in the Colab.
1 second. So if that's the repository, if I go on the first page over here, I get
can you scroll down? There is a link to Colab directly that you can link. If you go back to the repository, go back to the
if you
main
go back one and scroll
Yes.
down.
Scroll down.
Ah, yes.
Yep,
That's
right
it.
there.
Yes.
That's it. Okay.
Oh shit! I thought it would be on each notebook because a lot of them have that, you know, in the upper right-hand corner, and so I missed that table.
Now there is one
Okay,
thing
that's
over
all you
here.
got to do.
It's a shortcut for any GitHub notebook. You can change the github.com to GitHub to Colab.com, and this is a shortcut that any notebook you can also change that. There are different ways to do things.
Okay.
Okay.
So that's all
once
I
you
would have had to do with that URL. Nice.
Okay, so you change the runtime to change runtime type to GPU, and then you have to run the first few steps to
Uncommented. Yeah.
Ah, you're right. So let's stop that.
All right. So are there any questions about running a notebook in Colab and using a GPU that we still should answer before we move on? Does anyone have any questions there? Because it'll just run in Colab. You don't even need a GPU for the chapter, but whatever. So anyone have any questions about that?
Yeah, I think we are all
Okay.
good.
So, okay, good. So what I'd like to do is.
Do you want to show your book? Do you want to show your notebook?
Oh, I wanted to show you one thing though, because of what you were talking about. So Yakov, can you then? Do you have any model you've opened up yet successfully?
In a moment,
so what
yes.
you can do when you're done with that?
Installing.
Okay.
It's
So
installing.
go to that classifier you just instantiated, right? You got a classifier.
I'm still waiting for the notebook to install the software. Yes.
Oh, it's still running. Okay, yeah. Let me take over here. Is that okay?
Yes.
Okay, good. All right, so we'll just do this real quick. So I just want to show one thing before we go on and before we go through the chapter, which is, you can do this. You can go. So classifier. So I have the classifier is a, let's see what it is. Okay, so I've got a transformer pipeline, but I think you could just go model. I think that's what I did.
Yes.
And you could see, yeah, so there you go. When you do that, you could see the complexity. That's what I wanted to make sure you were aware of, that you can actually see that it's the Distilbert sequence, so I think it's just an encoder. There's no decoder in this one. And you could see every layer and the entire stack underneath it, okay?
Mm-hmm.
I want to show that. Okay, so with this chapter, I don't know with this group, it's kind of a basic chapter. So I was thinking that what we would do is go through, sorry guys, I'm going all over the place here. What I was thinking is we'd go through section by section, and I give just a really quick, my half-ass understanding of each section. But then I would think, depending on the experience of the group, that we could get people for each section that's of interest to us, that we can have people, ask questions of the group. I didn't understand this. I understood this. And maybe there's people that have a lot of experience with, LSTMs and with RNNs in the past, and they can explain their actual, experience of the difference between that and a transformer. So I think we'll just go through each section and discuss it and sort of summarize it. And, if it's not interesting, it's not interesting. But if it is, we'll get people's experience and thoughts on that. But before I do that, is there anyone else, who wants to just bring anything up that that maybe troubled them or that they found really exciting or interesting, that sort of thing. Well, we really should start talking about something if someone's very interested in that. Nobody have any initial first impressions other than Yakov? Someone's got to have an initial impression. I mean, I'm assuming everyone read it, maybe not, but you know, did anyone think it was just stupid or annoying or confusing? Any response at all about that first chapter?
It was pretty basic.
Before I go on. Yeah, it was pretty
it
basic.
was pretty basic.
Was there anything at all, Yuri, in it? Because you've gone through all this stuff before. Is there anything at all in it that was of interest?
I just want to point out, maybe people don't know that they have to unmute themselves. So maybe somebody wants to say something and you have to press on the mute button on the bottom in order to unmute yourself. So if you have any feedback, please unmute and say. Okay, no. Okay.
So was there anything at all, Yuri, that was stood out?
Yeah, for me, it's just like I understand now transformers. They are somehow kind of universal function or approach that can solve almost any, not only NLP problems, but they have been used in computer vision. I just understand from the chapter that the transformers are powerful and indeed in some way the future for NLP, because like all the state of the art stuff doing in NLP, they are based on transformers. So as the chapter is just basically introduction, that's basically what I can say. Thank you.
Yep. And so let's go into the first section here, right? And that's the first diagram. And they're just talking about what they're trying to do here is just talk about the evolution of the transformers and how they came out of RNNs and then ULM fit and evolved into two main strains of transformer models, which they show here in this funny diagram up top. Which I mean, it's kind of useful, but mainly you have your GPT-3 and your BERT style. So with the BERT style, that is trained on masking, word masking, and with the GPT language model style, those are trained mainly with next word or only with next word prediction. So they have two different forms of training the base model for those two different types of models. I think that's the main thing that's going on here. And was there anything else about this evolution and about this first section that you think they were trying to say that people should know? Anybody?
I can put in a shameless plug over here for the third chapter, which I'm going to volunteer to present, where we see the same graph with more details, that there are 3 lines, one of encoder models which read, which are like BERT, which has the reader, and the decoder or writer, which are in GPT. And then you have also models like T5, which have both the reading and the writing, which are good for translating. And so I have 3 actually lines, and we will discuss the internals, how the transformers work, how attention works in the third chapter. So there will be more details about the story.
Yep. So does anyone know when you train the BERT model, do you train it with the encoder and the decoder? I know you just use the encoder for when they train it. I think it's just the encoder, right?
Okay. Shall I just share the diagram? The thing is that this is one big, if you have a T5 translation model, we have one big model which has both parts, the encoder and the decoder. So if you train it from scratch, you have to train the whole thing from scratch, encoding and decoding together. If you want to do some transfer learning, you choose what you train and what you leave frozen. So, but yeah, it's really sort of, if you train the transformer or the translation model, it's one big model and you train everything. If you go from scratch.
Okay, so I guess that's pretty much all in that section. Now, the next section, which is page 2, by the way. If you've got your books, I hope everyone has a book. The encoder decoder framework, okay? And I think what he's trying to do is just go through a little bit of, first of all, a little bit of the history, which is that the big deal here, the big breakthrough was non-sequential processing. So you have a sequence, just a sentence or a series of tokens, right? So that sequence or that sentence, up until transformers, you'd actually process. You'd have one set of one vector, which you were just updating sequentially as you go sequentially through each word, right? So you're building context as you go through the sentence. And so you have a representation that has a hidden state that follows through, and then you have the initial representation or the trained representation of the next word in the sentence, but it gets some of the hidden meaning back from the first sentence, first word, and then your third word has some of the hidden context from the first and the second. But all along, if you looked at the dimensionality of the vector, it'd be staying the same, okay, as you're going through the sentence. And then at the end of the sentence or sequence, you have a representation that represents the entire sentence or the entire sequence. So problems with that are that they bring out, of course, if you have longer sentences or texts like paragraphs, or we get to documents, you lose the meaning. The value of the hidden state disappears over time. And so the old RNN and LSTMs had that problem to some degree, where you lose the meaning, you lose the signal of the context. Because, you know, in language processing, the context of each token or each word is very important for the meaning all the way through. So that was a limitation. That's sort of the main point is with transformers, that and the information bottleneck. So with transformers, they came up with a way of using self-attention, which means that you can actually process each word at the same time in parallel for a sequence, each token in parallel for a sequence, and still get the and do it in a way where you're actually infusing it with the context of the words around it. And the power of that is you get through what they call the information bottleneck, which means you can, you know, basically process a lot more sequences much more quickly because you're processing all the words in parallel rather than in sequence. Okay? And so somehow what they do, I don't know the details, but you do this self-attention for each word where you're paying attention to all the other words, and you adjust the embedding or the vector. So each word has its own, you know, dimensional and vector, and then after you take those and do the attention, you were going to combine them into one vector at the end. So just like with the RNNs, you do end up with one vector representing the whole sequence, but it's done in parallel, so it's much faster. And then they add multi-headed attention to that, which we'll talk about in Chapter 3, which gives it even more value, contextual value and meaning. And there's a bunch of other stuff. But I think that's the main point of the encoder decoder framework that they show here. And the interesting thing to me was that with RNNs, they had a concept of attention. So basically they made, even though they're doing the sequential cumulative processing, they call it sequential transduction or whatever, but even though they weren't processing in parallel each token, what they did is they made the hidden states available to the decoder, which they hadn't before. And so, and then because you had a hidden state for every single token in this process, you had a lot of hidden states, which is a lot of data, and the decoder could create even more problems with processing. And so they figure, well, if you have all of these hidden states, and when you're decoding, you're looking at each one of those hidden states, you need a way to pay attention to what matters, which hidden state matters. So I think that's where the idea of attention came out of, really before there were transformers. But the transformers changed the idea of attention to self-attention, which allowed parallel processing. So I know I'm sort of getting this half right, half wrong. So I think those are the main points of that section, attention mechanisms. Would anyone like to straighten me out or comment? I know this is all very basic, but no opinions, no point of views. So I got that wrong. Please straighten me out. If I got something wrong, it'll help me learn. Anybody? Chapter was very, very boring, or what? I found it informative, but does anyone have anything else to say about RNNs and about LSTMs and about the evolution of attention and self-attention and what it means? I mean, we're going to go into great detail in Chapter 3 and the actual mechanisms here. Just meant to give you an overview.
I think
really
you
matter?
said.
Yeah.
I think the key point which I take out of this introduction over here is that in the RNN world, you go step by step and you take only the final state, which means that you have to compress all the sentence into one vector, which where all the information competes against each other. So whereas in the transformers world, you keep for each word, for each state, you keep this information available for the decoder, and the decoder with the attention mechanism picks out what he wants to translate. So maybe can you scroll down to the diagram where you have the words of the sentence, the agreement on the European. Yeah, scroll down one more line to the diagram which we see at the bottom.
You want the heat
Can
map?
you just scroll?
You want the heat map?
Yes, heat map. Yes, exactly. So basically, the great thing is that when you translate this one sentence from English into French, that all the information from the input, I think it's French to English, I'm not sure. All the information from the input, like the French words, is available, and the output translator at each stage, he can pick whatever word he wants to base his translation on, and as a result, the information doesn't compete against each other anymore, and as a result, you get much more precise. It's much more easy for the network to make precise translations. So that's the big advantage of the.
Yeah, that makes perfect sense.
Yeah.
In the decoder, let me ask. I really don't have a intuitive understanding of how the decoder process works. I mean, it's too much detail to get in right now. But are you saying that does the decoder actually have access to the final hidden state of the encoder? What I need to know for sure is that does that have one multidimensional vector per word, per token, or is it combined? So you have to go back, and then does the decoder have access to the combined single? I think because the final state of all of these is like Bert's like 500 and something, dimensions. So they do combine it. So the encoder does combine all the words, all the tokens into one vector. I know you can go in and use it as an embedding and go back a layer or two and get to the actual individual word embeddings. But I don't know if the decoder does that. Does the decoder, it doesn't change your point, Jakob, but I'm curious, does the decoder look at the combined single vector representing the sequence? Yeah, go for it.
No. The decoder has one second, let me go back to the screen where we are. 1 second. No. What happens is the encoder produces one vector for each word. And the decoder has an attention mechanism that every individual word of the decoder and even every decision inside there, so that you have more than, can look at every output vector which they want. And the encoding is the attention mechanism focuses that looking on just what is relevant. So so as you see over here in the heat map, when the output, I think the output over here is August, when the decoder wants to produce the output word of August, it chooses to look mainly on the vectors which are a vector which is created by that word, which is the French word of August, and just translate that. Now, when you sort of in translation, you use so to say full vectors for the out of the input and pick whatever is relevant for that step of translation. And it can change the order according to the output order of the words, but even then, it just takes most of its input from the corresponding word if you have one in the input. Now, when you do text classification,
so I think you answered the basic point, which I want to make sure.
Yes.
My main question was if the decoder had access to the individual word embeddings rather than the combined embeddings from the encoder, and the answer is yes, that it does. Does anyone? Now, let me ask anybody. Does anyone have a contrary understanding of that, or can anyone confirm that? I mean, or make any comment on that? It makes sense to me. Yeah, that actually helps a lot. For me to begin to understand how the decoder works.
Therein will anything here unfortunately will be confusing until we get to the anatomy of the transformer, because that chapter will get into details, I presume. But the basic thing is that whenever in BERT, for example, if you have 6 layers of encoder, each one feeding into the other, and you have an encoder-decoder model, then for translation, for example, then what happens is that there are 3 sets of attentions at work. One is self-attention within the encoder. So each layer of the encoder pays attention to within itself. The same thing happens on the decoder side as well, which is the decoder self-attention, which is it pays attention to its own set of words. And then from every layer of the encoder, there is output into the decoder, and that's encoder-decoder attention. And so there are 3 sets of attentions at work when there is a transformer-based translation model. And to answer your question, yes, every word then goes into from the encoder to the decoder.
Okay. Yeah. And you're talking about training, of course. That's when there's...
Yeah.
Now, what I can
that
add,
makes sense. Thank you.
What I can add to the stem, if you use it, the encoder, like for BERT, not for translating, but for text classification, where you just want one combined output, then it is usual that people just look at the last line. Sort of that if you just want to have one output, then it is commonly used that you just look at the state which is created by the end of sentence token, and that this one state will include all the combined information of the sentence.
Yes.
But that's not used for translation. That's what you would do for text classification or anything similar.
Yeah. So for text classification, even when you're training, you only have the encoder side of the equation. So you don't have these 3 transformers that Srinivas was just talking about. You just have the encoder side, and the encoder side produces that one combined embedding. So that's interesting. That's good. Anyone have any more comments or questions about all of that? I mean, it's okay for us to get a very rough, start getting comfortable with the language before we get into chapter 3. I mean, that's...
The one other comment I would make vis-a-vis the RNN to or LSTM kind of models to transformers is, even though it's not inherently part of the attention thing, but what is fundamentally done in all transformers is this aspect of breaking up the single sequence into what is called heads or multiple heads, and the combination of self-attention and this breakup into heads actually helps you understand words in context even better. To give a very simple and oft-repeated example, it helps the model distinguish between the bank of a river and the bank where you keep cash. Because you use multiple heads, and also I think a little bit because of the attention, but more because the heads are split and then combined, and we'll get into the details of how that works in chapter 3. But that splitting allows more context and differential context, which the LSTM or RNN model is unable to do. So that's yet another
So I was
subtle improvement.
Yes, and I was really befuddled by the head, getting into an understanding of the multi-head attention part, and I think I understand it very roughly now. You could think of it simply, a very simple way, is you have a sentence made up of 10 words, or tokens, whatever, 10 words. One way to think of multi-head attention is you split that, you vectorize it all, of course, first, but you split the vector, or you split the sentence in half, let's say. And then you take every one of those 10 words for one of the heads. I mean, you use every one of the 10 words, but then you do a self-attention against one of the heads, which is the first 5 words. And then you take that same word and you do self-attention against the second 5 words in the sentence. And then that's really the fundamentals, I think, of multi-head attention. You split, and so you can get sort of like a different sense of the context of the word in different parts of the sentences by splitting it up. And that's the multi-headed part. And then you bring that all back together, and you have the same size vector that you had before for each word. Is that totally butchering it, or was it like 50% there towards understanding the
Yeah, it's 50 because it's the word itself and the words encoding itself which gets split. Single words encoding gets split through different heads.
But once you split the encodings, you have the mathematical vector representation. But if you look at the version where they show the size of the vector, it's you're splitting it, right?
Yeah. So, but the point,
but is the fundamental idea right that you're getting
I would say
self-attention
the fundamental
you're adjusting
idea.
your. Yeah. Sorry.
Okay. Now, actually, we are now jumping into chapter number 3, and I think at any time when it makes sense, we could say, well, just wait until we get to the chapter. But the answer to your question is like this: you have one head of attention does the following thing. You have some input information, which is sort of many words, the vectors of each word or each token. So you have a list of input tokens, and the attention mechanism selects which of these words are relevant for the current decision which you want to make, and applies a decision. So it selects and combines 10 words into one vector. That's what attention does, where it says it gets a rule, pick this word, it's relevant for me right now. Now, in the transformer reader, sort of the encoder, every state, every input vector goes through many of these attention steps. First of all, you have 12 parallel steps which do attention. They're called heads in the first layer. So if on layer, we have 12 parallel decision units, and each decision unit independently looks at all the words of your sentence, pulls out what they think is relevant. So one unit could say the first word in the sentence is relevant for me, and the parallel unit at the same time, the second unit could say, but for me, the last word of the sentence is relevant. So they pull out whatever they think are relevant for them, and they combine their decision. And then you have the next layer, which does the same thing. You have again 12 heads, where each head pulls out what is relevant for him. So you have 12 times the number of layers, decision units, which each one combine whatever information they have. So it's like I understand that each head is one decision unit, and then you just stack as many as you can, 12 times the number of layers, into a system to give the neural network enough power to decide, and they use the power in whatever sense fits best with the data. So I want to repeat the last picture. So basically, you have a parallel set of many decision units, 12 in parallel, which are called 12 heads for each layer. And then you have another layer with another 12 decision units, and again. And every individual decision unit gets as input all the vectors from the words which you have, and they decide what you want to apply to. And so having a lot of decision power in the system enables the neural network to fit the data in the best way to make the right decisions. Does it help you, this explanation, or is it confusing?
Yeah. I mean, this is a little bits and pieces of discussion have helped me. And again, we're getting too detailed into chapter 3, so I'm ready to back up and go back to the next section. I think someone had a comment though before. Comments before we move. So, go ahead and speak up if you do. But so the main thing is just start used to the idea of attention, which a lot of us already are, obviously, but to the ideas of attention, self-attention, and the whole encoder decoder framework. So they're just sort of like priming us for for the rest of it. And I think the next section is transfer learning in NLP. And I guess this was pretty revolutionary when it started happening with ULM Fit and then with transformers. Does anyone have anything they want to bring up in this? Is there anyone else who wants to describe transfer learning briefly, or has a question? I guess if anyone has a question, that would make a big difference. So can someone tell me what transfer learning is, other than Yakov? Well, because I'm sure we'll have you supplement with someone else, how someone else would summarize it. But I want someone to just, maybe this is kind of basic for everyone, I don't know. But if it is, I want someone to give me their idea of what transfer learning is and why it even matters. I want somebody. What is transfer learning? Somebody tell me. Who cares about transfer learning? Go ahead, Yuri.
Okay, so so transfer learning was traditionally used on NLP tasks where you had giant amount of data, like a ImageNet type of data, where you trained your networks, and then instead of solving your own problem and training from scratch, you could reuse the weights that were trained on the larger problems and just have a very small amount of labeled data for your problem. And it's been done, you can typically do it with either like changing the head and training just the head, or retraining few layers, or retraining the whole thing. And yeah, network, it was like amazing that it was not ever applied to NLP till recently, and now it's the most common way of doing it. So basically, you train your network on the giant problem that's not related to you, or you let Google or some other big company to train the network, and then you just reuse the weights, and either if the problem is exactly the same, you don't need to change the head, or if the problem is different, you change the head, and then you just start optimizing from much closer solution.
Yep. And before that, right, old school NLP, you just train your own model, even like Word2Vec. You have to have all your own data. You train your own model, which is very efficient with Word2Vec. Uncontextual, if that even. But now you basically, like, I bet nobody on here has like trained their own BERT-based model, or because it's just huge, right? Some people do it, but in general, you don't train your own base model anymore. Someone else's base model, like curiosity, you just stuck in the weights. And practically, that's the whole Hugging. That's not the whole thing, but that's really what Hugging Face Library is centered around, like how it exploded, I think. Have the just choose different base models. Yes.
Do you remember why? So I remember at some point I understood why you couldn't do transfer learning with Word2Vec or FastText, but now I don't remember why.
Well, there was no transfer. learning mechanism, right? I'm not sure I understand the question. Oh, transfer learning. I'm sorry. I was thinking self-attention. Yeah. Transfer learning, why could you not do that? Well, actually, I think there was no, that's a good fucking question, because there were models you could just download. Like, remember there was the word Devec from Google? And I remember getting it through Spacey and through, you could get them through Densum. So you could use other people's models, but I think updating the models was the problem. And I don't know, I know in the past updating the models was a problem because of the exploding, exploding
I think it's
yes.
A combination of things here, right? Like if we step back in history, and the reason they introduced ULM fit in this chapter is because Jeremy and Sylvain were the first people to, there was a belief, transfer learning existed in the vision world for a long time. So people used to train models on ImageNet and then use the same model trained on medical images, for example, and they found that if they had to spend all their energy and effort to train the model from scratch on medical images, that you could argue it worked better, but it was not all that better, and sometimes the ImageNet trained models still performed a lot. Obviously, speed was a benefit, but also they sometimes perform better. So in vision, it was kind of taken for granted that transfer learning worked. And Sylvain and Jeremy were pushing the idea of using transfer models in language. But at that time, the state of the art was just vector-based, like, GLOVE or Word2Vec and stuff. And in those instances, the belief was that you needed to train the vectors on the corpus that you needed to predict on in order to get the best results, and transfer learning as a concept would not work. And there wasn't empirical data, it was just a belief of people who were still heavily influenced by linguistics and the belief that language just modeled with vectors wouldn't translate from one domain to another. That kind of held back. And also the fact that at that time there was just this vector-based model. The further improvement towards using many layered RNNs, LSTMs and stuff was still in progress. And I think ULM Fit was the first LSTM-based model, multi-layer LSTM-based model that actually demonstrated that transfer learning could work in NLP as well. And simultaneously, or I don't know, within a short time, the whole thing about BERT and transformers and all that came about and completely blew the belief apart that transfer learning couldn't be applied. And now it's so much the norm that we even forget that transfer learning at one time was believed to not be applicable in NLP.
Yes, that wasn't that long ago. The interesting thing about it is that Word2Vec, right, non-contextual, before BERT came out in Alberta or whatever. So that, I think couldn't you load the Google one then update it? I don't know, but the main thing is that I think there's two reasons that transfer learning didn't matter much, because first of all, you could train a Word2Vec model, a non-contextual model, on your own data at scale quickly, right, Yuri? I mean, that was not hard to do. You didn't need to use other people's models. I mean, I think there's two reasons transfer learning really matters now. Is one, neural networks are expensive and annoying and time-consuming to train, right? So, and number two, because of the self-attention, multi-headed, all that the transformer stuff, the models are better to start with than your own. Like even now, if you had unlimited computing power, you probably wouldn't you'd just be building your own, models willy-nilly because they're so huge. Right. So, but it is interesting. Yeah, and there was also the vanishing gradient. Once you got into the neural networks, there was a vanishing gradient problem, I think, so what happens is you have really fragile, so if transfer learning is practically useless unless you could fine-tune it. It's not totally, you can use it as embeddings, but they had to solve the fine-tuning problem, right? Then make updating models stable enough. Gary, was that your question in general, or were you trying to answer something a little different than what was?
Yeah, actually, I was thinking of more like a specific issue. So let's say you're only interested in embeddings, and you want to and you want to take pre-trained model, like let's say word-to-back style model. I don't remember if there was no mechanism for fine-tuning, so you couldn't like.
Why is
I remember there was some problem that basic even and I don't remember if fast text was better or not. I think it was also not trainable, but I don't remember what was like. Is there like some reason that was prevented?
Yeah, and it can't be the vanishing gradient, and it can't be the vanishing gradient problem because it's not a deep neural network really. Oh, they use method to skip grant.
Maybe I can add some perspective here. I listened to the Fast AI lecture a few years ago, and there Jeremy was complaining that people in academia sort of all think in the same way, and people say we don't do transfer learning. It's an idea from image processing and doesn't work. And I think to make it work, somebody actually has to do the work right. Sort of, you don't download a library which nobody has written, and even if you do a quick experiment, if you don't apply the care of actually make it work, it won't work. Sort of, you can make so many mistakes. So I think that Jeremy said people are stupid. Everybody goes in the same way, and nobody tries transfer learning. It's stupid. Let's just do it. And I think that Jeremy said, let's do it, and he did it carefully and succeeded. So he was the first one which opened the door. And after he opened the door, everybody went through the same door. But you need somebody to actually to do the work. Now, it's not so trivial. As you see with the ULM training, you have two steps. You take first, you take a model which is trained on a huge data set, and then you say, now I transfer learn it on my language without labels, and then I transfer learn it on the actual problem with a much smaller set but with labels. So, and to do this whole step correctly, you need confidence that it will work, and you need an expert like Jeremy to do it, and then you need to publish the results, and people need to pay attention to that. So just Jeremy was the first one who says, well, it's stupid not to do it, let's do it. Many other people, many researchers just follow and improve what already is out there. But to take the courage to take an idea.
That's exactly that was exactly Srinivas's point. So you basically, they're making a somewhat not the most satisfying answer, because I'd like a technical answer, but I think it totally makes sense. I think that it was a cultural answer that someone could have done it if they wanted, but I think there's two sides to it. I think it's not just a human nature, academia, culture thing, which obviously it is, but it also was back then you could just word-to-vec your own data. It was just easy, and also it wasn't as valuable to do transfer learning back then. I think it's those things combined. Jeremy breaking that, seeing the opportunity in front of his face and going, "The emperor wears no clothes, motherfuckers," and he goes for it, right? And then he made it work, him and the other guy, and combined with the fact that transfer learning now means a shitload, right? To anybody who's doing NLP, because there's so much value in using someone else. Okay, that was interesting. Okay, so is there anything else on? I mean, they're bringing it up because the whole Hugging Face library is predicated on the value of transfer learning. So is there anyone who has any really basic questions? Because we've been talking sort of more on a experience. People who have some experience. Is there anyone who has any more basic question on what the heck transfer learning is? I know, Yuri, you described it very simply and in a very straightforward way, but sometimes people need to hear that a different way. So is there anyone who's just like, what the hell is transfer learning? Bill, or any other questions before we move on to the next section? Okay. So, so then they just get into, they're trying to get us into the more the Hugging Face framework here, and a tour of a transformer. Yeah, Hugging Face transformers, bridging the gap, and so they're going to show you, give a very brief overview of basically all the different, or many of the different pre-canned tasks they have for you and how easy they are to use. And so they show you text classification, name entity recognition, question answer. I mean, in a way, you know, it's accepted now, and I've gotten really used to it. But the fact that you use one library and all these different models and solve all these different NLP problems, you could actually use a Roberta. You could solve probably solve almost all of these except for the text generation, right? I mean, it's pretty revolutionary, and they wrapped this whole revolution up in a library. That's the main point here. Does anyone have any distinct or specific questions about any of these tasks that they go through here? Very briefly, and summarization as well, and translation. So they're just showing off here. So you could do everything, including text generation. Does anyone have any comments or questions?
Yeah.
Has anyone go ahead, please.
Yeah. So just as you have seen now how transformers are powerful, they can do many tasks. Can we discuss about some of the challenges they discuss about? For example, one of them they discuss is working with long documents, right? So transformers, for example, self-attention, they said works really well with just a simple paragraph like a text, but it becomes really difficult for transformer to understand longer text like the whole document. So does anybody knows something on top of these?
Yes, maybe.
Does anyone have any experience actually using this stuff with long documents? Go ahead, Yakov.
Okay, I don't have any experience with long documents. I can explain the answer over here, the reason why it is, because in the self-attention layer, every word can look at every other word. So if you have 5 words, that you have 25 pairs of attention which you have to decide whether you take into account or not. If you have 10 words, you have already 100 possible combinations, and so does the number of combinations of possible attentions scales quadratically with the length of the document, which means that it goes slower and slower over time and uses more memory on the system. So now there is at least one architecture where people try to address that problem by saying, let's change the attention in a way that you pay attention most to closer words and not to all of the words, and then the problem can be resolved. So the answer is it's simply scaling of the number of potential possible combinations which would have to be taken into account. It becomes a heavy problem. Like if you studied sorting and you have this simple search where just swap 2 numbers next to each other, and it's quadratic. It gets slow over time the bigger the words get. But if you have a more efficient sorting algorithm, it scales much better. So the basic self-attention algorithm is scaling badly, and there is this Big Bird, I believe, is one example where they specifically changed the algorithm to have more scalable attention algorithm, and then it works for larger documents as well.
So
that's what I
basically
can add.
Yeah.
Long form, yes.
Yeah, I think long form is another one. So to answer the question a little bit in a different way, there are some models that try to address it. I don't know if I've talked with anyone who has used them and how well they perform, but in general, there's all sorts of tricks people use. We'll split the documents, maximum characters you can, or maximum tokens. Split them up, and then you embed, you run them through the model, and you combine them back together. Use those embeddings for your task. That's one way. People. Another way is you use a summarizer, which you summarize the document. And actually, this is maybe not scalable, but I'm a GPT-3 freak now. OpenAI just. But ideally, you could sort of accurate summarization that gives you a big, full summarization with GPT. Many ways to do it, including using any. Some people do that, I think. Summarize to the down to the size that you need to go down to, which you're going to lose some information. I think there's a couple other ways. Remember what's his name? Yuri, the McCormick. Does these great tutorials. He went through like 5 or 6 other ways. Does anyone have any other experience with how you deal? Basically, it's not a solved problem. I don't think it's a fully solved problem. There's some ways around it that are somewhat effective. I don't know if there's something new I've missed where now someone solved this. But does anyone have any? Mike McCormick, I think it's.
No, the latest I've seen is, and I'm trying to find a reference now, sort of people do this, they understand that they build understanding, like let's say you're doing summarization, you can't do it on the whole document, but you do it like you do a sliding window through the document, basically, and you, so you get like a sequence of understanding. I'm trying to find. I never use it myself. I think Stanford uses that technique. I'm trying to find the reference.
You're talking
but
about
again, it's chunking.
a sliding window. You're talking about for summarizing, a sliding window for summarization.
I think it's for summarization. I'm going to try to find the reference.
What I
but
can
so,
say,
yeah, basically,
the goal
is chunking.
To summarize without. Yeah, go ahead, Yuri. I'm sorry.
Yeah, idea was to chunk it and kind of perform your NLP task on the sections and then make conclusions from that sequence of summarizations.
Yeah. So the answer is it gets a little complicated, and there's ways to deal with it.
I think in chapter 9, when they, I'm not sure whether it's chapter 9, when there's a searching, or maybe 7, let me check. I think chapter 7, question answering, there they use, break up longer documents into smaller chunks and search in each chunk separately. That's one example in the book.
Yeah, which you could see with question answer, because you could have multiple contexts, right, or multiple. That's the documents you're pulling from. But for a classification problem, somehow you have to, represent the whole thing. And that's where you'd want to somehow separate them, then bring them back together before the task. Split it up and then back together your embeddings before your task, or use some sort of clever summarization that's not very lossy. Which could use GPT-3 for. It may be a little expensive. Definitely will do that.
But GPT-3 is also not scalable.
Sliding. Yes. Well, I mean, it's expensive. I mean, yes. I mean, you could just.
But
hit
it has the same problem.
The OpenAI.
But it has the same problem. So if you GPT-3, can GPT-3 handle a huge document?
Right. You're right. It has limitations. 4,000 characters. I think it's more than BERT, but it's like 4,000. So it's bigger. That could actually save your ass completely, but it also may not be big enough for your PDF documents you're dealing with. You're right. Yeah, absolutely right.
Yeah.
But there's ways to solve that. In fact, I'm sorry, as I was saying, there's this guy Shapiro who does these videos on GPT-3. And he actually summarizes entire books, and you do recursive summarization. He did it for Alice in Wonderland. You just chunk it up and summarize each chunk. Take those summaries and summarize them. And he was able to condense it down, if you want it. You don't have to go this far, but to two sentences, and they were really good. 2 sentences. So you can use recursive summarization with GPT-3, and I've seen it done, and it's amazingly good. So, I mean, not from a quantitative point of view, but just from, I mean, I don't think it's been tested. I could say it's the best, and it has a benchmark, but it looks very good. Sorry, I think Shamsun, you're going to say something?
No, I just want to say thank you for discussing on this point. Thank you.
Yep.
Okay.
Good.
I think.
Thanks for the question. That was good.
Yeah, we are already on top of the hour. If Darren, you're done with I'm not sure. But people, the session, as we said, is an hour. But if we have more content to go through, then yeah, feel free, Darren, to continue. Yeah.
Yeah, I mean, I don't think we have any more content. I mean, it's a pretty content. I mean, it was kind of thick in a way, but it was thin. This is not much of a chapter, really, in terms of technically at all. So I guess unless anybody has anything else they want to bring up, is there anything else? Just can't get off your chest, do it now. Otherwise.
Oh, I wanted to mention one thing. So I was gonna use Colab to do, to follow the book, but I've noticed that they give links to Gradient and SageMaker, and they're both free, and they actually say that you can get better GPUs with those. So in the same table in GitHub, they have like 2 more links for each chapter. I think for SageMaker, you have to like wait for the approval. I think Paperspace, I had it from before. So I'm trying to figure out how to get like a better, how to request a GPU. But that might be like a better free GPU for the course than Colab.
Okay,
because they're saying like now you get like a K80 typically with Colab, which is not the greatest.
Yeah, and probably when we get to the later chapters where we're fine-tuning and then actually building from scratch, that'll matter a lot, right?
Okay.
Was there anything else? Yeah. Okay.
I just want to mention that we have chapter 2. Anybody here wants to present chapter 2, which is basically text classification, is still Bacon. If you want to present that, please do so. Yeah. I think we have a couple of sign up. Almost we have the chapters being signed off. Yeah. Only few. So feel free, please, to sign up for the next chapter, chapter 2, test classification, and where we'll start seeing the real, I think, the protocol of the book. Today, the chapter 1 is just introduction and the history, how transformers work. But we will indeed see the anatomy of the transformer, which we briefly discussed today during the session, but we'll see the details chapter 3. And I can see your cop has signed up for the anatomy of the transformer. Thank you for that. And Yuri also signed up and David as well. So yeah, thank you all for signing up.
Thank you very much for organizing it, and Darren for guiding this discussion on the chapter 1.
All right. Thank you. Darren, if there is nothing, there is no question. So we can anything you want to add, Darren?
Oh, no, that's it. We're done with the chapter.
Okay.
Sure.
All right. So anybody with question or something to add before we go on? Right. So it means we are all good. I think thank you very much for joining us today. We see next week the same time for chapter 2. Thank you.
Talk to y'all later.
Bye-bye, ciao.